morning. Welcome to the lecture series of operating systems. In today's class, we try to discuss about the semaphores. So, what is the definition of a semaphore? A semaphore S is an integer variable. Apart from its initialization, its value is accessed only through the two functions. One is wait and another one is the signal. So, the semaphore is an integer variable. We can assign any value at the time of the initialization, but its value is modified using the two functions. One is wait and another one is the signal. We try to discuss about the wait operation was originally termed as P, and similarly the signal operation is originally termed as V. That is nothing but the semaphore, wait and signal functions. In some textbooks, they referred as P is representing the wait function and V is representing the signal function. Now we try to discuss about the wait and signal operations. So the wait is one of the predefined function, and its main purpose is it is used to decrease the value of the semaphore. For that reason, the wait function takes a parameter S as a parameter, and it is nothing but a semaphore. And in this wait function, first it verifies the S value is less than or equal to 0. If S value is less than or equal to 0, without performing any operation, it is in the while loop only. That is nothing but the busy waiting. That is without decreasing the value of S, because it is already its value is less than or equal to 0. For that reason, whenever any process called the wait function, if the semaphore value is 0, so automatically the process is in the busy waiting. When this condition loop will be terminated, if S value is greater than 0, then the condition is false, it terminates the while loop, and S value is decreased by 1 and the function will be terminated. So automatically the wait is one of the function, it takes a semaphore as a parameter. If whatever the parameter we are passing, if its value is greater than 0, then the semaphore value is decreased by 1. If the semaphore value is already 0, then automatically that process is in the busy waiting. That is, some other process increases the semaphore, then only this process comes out of the wait function. And the another one is the signal function. What is the signal function? The signal is also with the another function modify the semaphore, and it takes the semaphore as a parameter, and it simply increase the semaphore value by 1. So automatically there are the two functions, one is wait and another one is the signal. The signal function is a simple implementation, the semaphore value is increased by 1, but the wait function is, if already the semaphore value is greater than 0, its value is decreased by 1. If already its value is equal to 0, in that case, which process called the wait function, it must be in the busy waiting until the semaphore value is greater than some other process modify the semaphore, then only its value is decreased by 1 and comes out of the wait function. Now we try to discuss how we are able to use the semaphores. So we try to discuss about the types of semaphores. There are the two types of semaphores are available. One is the binary semaphore and another one is the counting semaphore. Already we know that binary number system. What is the possible values of the binary number system? Either it may be the 0 or 1. So automatically in the binary semaphore, it is used it consisting only the semaphore value either 0 or 1, and the binary semaphores are mainly used to implement the process synchronization problem. That is nothing but if any process wish to enter into the critical section, then in that case they are using the binary semaphores. And another kind of semaphores is a counting semaphores. The name itself indicates that it is allowed to count how many resources are available. So example of the counting semaphores is, for example, an operating system is having the 10 instances of a particular resource type. We are assuming that one resource type is having the 10 instances. So automatically the initial value of that counting semaphore value is 10. Before allocate any resource, it simply called the wait function. If the semaphore value is greater than 0, it is decreased by 1 and the resource is allocated. So automatically it is allowed to allocate 10 resources. Once it is allocated every time, the semaphore value is decreased by 1. Once it reaches 0, indicate that all the resources are allocated to the different processes. If any process requires some more resource, then call the wait function, it is in the wait, because then there is no more resources available. Similarly, any process release the resources is simply called the signal function. So semaphore value is increased by 1. So automatically The counting semaphores are used by the operating system to maintain how many resources are available at that particular time. For that reason, the operating system uses the counting semaphore. So, I assume that you understand there are the two types of semaphores. One is the binary semaphore and another one is the counting semaphores. The binary semaphores are used for the process synchronization purpose. These binary semaphores is consisting only the two values, either 0 or 1 only. And the counting semaphore, initially we can assign any value, and generally it may be based on the number of instances are available, we are allocating that number 10. If the 10 instances are available, we are allocated 10, and it simply used before allocating the resources, it called the wait function. After releasing the resource, it called the signal function to maintain how many resources are available at that time. The semaphore value gives that how many resources are available at that time. For that purpose, we are using the counting semaphores. Now we try to discuss about the how to use the binary semaphores to achieve the process synchronization. Here we are assuming that mutex is a binary semaphore. Mutex is a binary semaphore. What is the binary semaphore? Its value is either 0 or 1, and initially we are assuming that its value is 1. Mutex is a binary semaphore, its initial value is 1. And to achieve the process synchronization, in the entry section it simply uses the wait mutex, that is the entry section code. Once it is completed, the process comes out of the wait function, it is allowed to enter into the critical section, and the exit section code is nothing but the signal of mutex and the remainder section. So, it is very easy to implement using the wait and signal to achieve the process synchronization. Now we try to discuss this algorithm satisfies the progress, mutual exclusion and bounded waiting. We try to verify. So here in this example, initially with the mutex is a binary semaphore, its value is 1, and we are assuming that P1, P2, P3 are the processes. We are assuming that P2 process first wish to enter into the critical section. Already we know that mutex is a binary semaphore and it is shared by all the processes, and its initial value is 1. And whenever the P1 process wish to enter, P1 process called the wait mutex. What is the mutex value? 1. Whenever the P2 process called the wait function, mutex is set to 0 because already its value is greater than 0, it is decreased by 1 and comes out of the wait function. For that reason, P2 successfully completes the wait function execution and P2 entered into the critical section. Then automatically, already we know that mutex value is 0 and P2 entered into the critical section. If P1 wish to enter, again the P1 process called the wait mutex, mutex value is 0 and P1 called the wait function. Already in the wait function implementation, if the semaphore value is 0, automatically it is in the while loop only. That is the P1 process in the busy waiting, it is not comes out of the wait function. So automatically P1 is not allowed to enter into the critical section. Once the P2 process completed the critical section execution, in the exit section, it simply called the signal mutex. What is the signal mutex? The mutex value is increased by 1. So automatically, the P2 completed the increased by 1 and P2 entered into the remainder section. Now the P1 called the P1 in the while loop only. So automatically the mutex is 1. For that reason, its value is decreased by 1 and P1 is entered into the critical section. So automatically, using the wait mutex, we are able to implement the mutual exclusion. The reason is mutex is a binary semaphore, its initial value is 1. First, which process wish to enter, that process comes out of the wait function and mutex set to 0 and that process entered into the critical section. If one process already in the critical section, then mutex semaphore value is 0. If any process wish to enter, they are in the busy waiting and they are not allowed to enter into the critical section. For that reason, this algorithm satisfies the mutual exclusion condition. And next, this algorithm is also satisfy the progress condition. The reason is, once the process completed the critical section execution, it simply called the signal mutex. And based on that one, mutex value is increased by 1 and automatically which one of the waiting process is allowed to enter into the critical section. So automatically this algorithm satisfies the mutual exclusion as well as the progress condition. But whenever we consider about the bounded waiting condition, just like the previous problem, that is nothing but the previous hardware synchronization constructs, how they are not satisfying the bounded waiting. For example, P1, P2 are the highest priority processes and P3 is the least priority process. P1 and P2 continuously allowed to enter into the critical section, P3 may wait for a long period of time. I hope you understand this algorithm satisfies the mutual exclusion as well as the progress. Just like the hardware synchronization construct, it is not satisfy the bounded waiting. The reason is we are assuming that P1, P2 are the highest priority processes and P3 is the least priority process. There may be the possibility P1 is allowed first, followed by P2, followed by P1, P2 and so on. P3 may wait for the long period of time. To overcome that one, just like the hardware synchronization construct, we are using the waiting array, and using that waiting array, it is possible to eliminate the bounded waiting condition. I hope that is considered as an assignment, and please provide the solution to satisfy the bounded waiting condition also. Next, we try to discuss one more example where we are using the binary semaphores, another example. We are assuming that P1 and P2 are the two processes. Example is P1 process task is they need to transfer the 1,50,000 rupees. So we are assuming that Kumar is a bank account and his balance is 1 lakh rupees. And his friend Sunil, he want to transfer the amount 1 lakh rupees to the Kumar account. So once the amount is credited to the Kumar account, his balance is changed to the 2 lakhs. And he want to purchase an item, Kumar want to purchase an item and its cost is 1,50,000 rupees. Its cost is 1,50,000 rupees. For example, we are assuming that the Kumar want to purchase a product. To purchase the product 1,50,000 rupees, that transaction we are assuming as P2 process. And the P1 process is to transfer the amount, that is the amount from the Sunil account to the Kumar account, 1 lakh rupees is the P1 process code. And what is our requirement? For example, Kumar balance is 1 lakh rupees and his friend is transferred the 1 lakh. Once the amount is credited to the Kumar account, then only he allowed to initiate the transaction to transfer the 1,50,000 to the merchant's account. If before crediting the 1 lakh rupees, if he try to transfer, the transaction is declined because his balance is only 1 lakh and he want to purchase the 1,50,000. So automatically the instructions to transfer the amount from the Kumar account to the merchant account, we are assuming that those statements are S2, it will be executed after the amount is credited from the Sunil account to the Kumar account. We are assuming that those transaction code is represent the amount of code transferred from Kumar account to Sunil account to the Kumar account is existing here. After completion, that is after the amount is credited, they simply call the signal mutex. And here also we are using the wait mutex. We are assuming that mutex is one of the binary semaphore and its initial value is 0 for this problem. What is the problem? After the amount is credited to the Kumar account, then only the Kumar is allowed to transfer the 1,50,000 to the merchant account. So these are the amount transfer from Sunil account to the Kumar account is one process, one program, and the Kumar account to the merchant account is another program, but there is a need of the synchronization. After receiving the amount only it is allowed to transfer. For that reason we are using the mutex is a binary semaphore, its initial value is 0. After crediting the amount from the Sunil account to the Kumar account, they simply call the signal mutex. What is the meaning of the signal mutex? Already mutex value is 0, once it calls then only it is set it to 1. And whenever the P2 process, Kumar want to transfer the account, first it verifies the wait mutex. Initially mutex is 0, before crediting if we try to execute, it is in the wait loop only, that is the Kumar, this process is not allowed to transfer the amount from the, this process is not allowed to transfer the amount from the Kumar account to the merchant account. Once the amount is credited, then only it called the signal mutex, then only this process is allowed to transfer the amount from Kumar account to the merchant account. In this way, to achieve the synchronization purpose, we are using the binary semaphore mutex. So I hope you understand. The mutex is used in the previous example. Before allowing to enter into the critical section, we are using the binary semaphore. Similarly, if one of the instructions must be executed after completion of this a set of instructions, in that case also we are using the binary semaphore. This is the another example how we are able to use the binary semaphores. The another one is the counting semaphores. How we are able to use the counting semaphores? Generally, the counting semaphores are used to count the number of given resources are available in that one. So automatically, for example, we are assuming that there are the 10 instances are available of the 10 printers are available. If any processes request it, they simply allocate the printer. For example, we are assuming that the server is having the 10 printers, and before allocating the printer, it's simply called the wait count. Initially, we take the CNT is one of the counting semaphore. Its initial value is 10. If any process request, it's simply called the wait count. The count value is decreased by 1. And the process printer is allocated. In that way, it simply allocates up to the 10 times. So automatically it is 10 is decreased to 9, 8 and so on. 1 is converted to 0 after allocation of the 10 resources. Similarly, for example, if any process releases the printer, it simply called the signal count value is increased by 1, 2, 3 and so on. For example, all the 10 instances are allocated to the different processes. If a process requests one more printer, then simply call the wait function. If the count is equal to 0, this process must wait until some of the process release the printer. Then only the printer is possible to allocate. In that way, the operating system uses the counting semaphores to allocate the resources to the different processes, and it is also able to, for example, at some time, the CNT value is equal to 5, indicate that there are the 5 instances are available in the system and the remaining 5 is allocated to the different processes. So automatically the counting semaphore is simply indicates how many resources are available at that particular time. We are able to get the results. So this is the usage of the counting semaphore. So the next one is we try to discuss about the semaphore usage without busy waiting. In the previous wait implementation, the wait of semaphore, if the semaphore value is less than or equal to 0, without performing any operation, the process is waiting. So automatically at the waiting time also the process utilizes the CPU cycles. So to avoid that one, if any process wish to enter into the critical section, if some other process performing the operation, this process need to wait, but it is not allowed to use the CPU cycle. These cycles may be used by the some other process. So this process need to be suspended until one of the critical section process completed its execution, then only it is allowed to revoke. For that reason, this is the another implementation. The advantage of this one is it is possible to save the CPU cycles. So here the implementation is we try to define a semaphore. It is one of the user defined data type and its value is consisting of the int value. And next one is it is a list is one of the list of processes are waiting for the particular semaphore. Initially its value is equal to null. And how to, so automatically now we are defining the semaphore is one of the data structure. It's consisting of the integer value. In addition to that one, what are the processes are waiting for the particular semaphore, that process IDs are also be maintained in the semaphore. And next one is we try to implement the wait and signal function. What is the wait function? In the previous wait function is if the semaphore value is less than or equal to 0, it is in the waiting loop. But here in this one, with the semaphore first, then only the semaphore value is decreased by 1. But here in the modification is directly the semaphore value is decreased by 1. What was the value in the previous one? If it is greater than 0, then only its value is decreased by 1. But here without comparing the semaphore value, its value is decreased by 1. And once the semaphore value is decreased by 1, now we are verifying if the semaphore value is less than 0. If the semaphore value is less than 0 and which process call the wait function, add this process to s dot list. That is nothing but which process call the wait function, that process is added to the semaphore waiting list. And block means this simply the process is simply suspended. Example is P1 process call the wait function. Already the semaphore value is 0. Then automatically s value is decreased by 1. It is set to -1. And the P1 process is added to the s dot list and P1 process is blocked. That is P1 process is not utilizing the CPU cycles. So this is the wait function. For example, already s value is greater than 0, its value is decreased by 1 and with this condition is false. For that reason, directly it comes out of the wait function. Now we try to discuss about the signal function. In that signal function, just like the previous signal function, the semaphore value is increased by 1. After increasing the value, we are verifying if the semaphore value is less than or equal to 0, when its value is equal to less than or equal to 0, if some other processes are waiting for this semaphore and they are suspended. In that case only s dot value is less than or equal to 0. we simply remove a process P, that is one of the processes are waiting from the S dot list, we remove and we are assuming its name is P, and we wake up P, that is nothing but P process is revoked and it is allowed to continue its operation. So automatically if the sum, whenever we call the signal function, its value is increased by 1. In addition to that one, if some of the processes are waiting for the particular semaphore, one of those processes are allowed to enter the critical section. So that is the advantage of the signal function. Implementation is just similar to the previous one only, that is wait of S, critical section, and signal of S, remainder section. And next one is we try to discuss about the limitations of the semaphore. One of the main limitation of the semaphores is the deadlocks. There is a possibility of the deadlocks and starvation is existing. For example, we are assuming that how to the deadlock is existing is, we are assuming that there are the two semaphores. Yes, we are using the two semaphores, S and Q, and these are both are the binary semaphores and its initial value is 1. And the P0 process using the statements wait of S, wait of Q, and there is some critical section, and signal of S, signal of Q. Similarly, the P1 process uses the wait of Q, wait of S, and some critical section, signal of Q, signal of S. We are assuming that both the processes are started at the same time. P0 executed the wait of S and P1 executed the wait of Q. So what happens? P0 completed the wait of S, S is set to 0 and it comes out of the wait function. At the same time, P1 call the wait of Q, Q is also 1 is set to 0 and it comes out of the wait function. So automatically P0 executing the wait of Q. What is the Q at that time? It is 0. For that reason, P0 is waiting for the wait of Q. Similarly, P1 call the wait of S. Wait S is also 0, it is waiting. That is nothing but P0 is waiting for the P1 releases the Q, because P1 calls the wait of Q. Then P1 is allowed after completion of the critical section only, it gives the signal of Q. For that reason, P0 is the process is waiting for the completion of the P1. Once P1 is completed, it gives the signal of Q. Then only it is allowed to comes out of this wait function. Similarly, P1 process is waiting for the S semaphore. That lock is placed by the P0 process. After completion of its execution only, it calls the signal of S. So automatically P0 is waiting for the P1 process completion and P1 process is waiting for the P0 process completion. Both are waiting. That is nothing but the deadlock. So one of the main limitation of the semaphore is, there is, if the program is not implemented properly, there is a possibility of the deadlock is existing. So what is the another limitation? For example, if the semaphore is not used properly, for example, generally what is the, we are using the mutex is a binary semaphore and its initial value is 1. We are using the wait of mutex, and another one is the critical section, and next one is the signal of mutex, that is the exit section of the, and next one is the remainder section. This is the code we are using. For example, someone uses the signal of, or someone uses in the place of the wait itself, they call the, in the place of the signal they call the wait of mutex, that is they are not used properly. So automatically it is not possible to comes out of the wait function. So there is a starvation, that is one process only, P1 process. Actually they use the wait of mutex, critical section, signal of mutex, remainder section. If the programmer instead of the signal function, he replaces the wait function only. So at the time of wait function, this mutex is set to 0, it enters into the critical section. Generally it need to call the signal function, but instead of the signal he replaces with the wait function. So it is in the while loop only, busy waiting only. So automatically there is a possibility of the starvation is existing. So if the he is not properly used, then automatically we get the problem. Similarly, in the place of the wait, he simply uses the signal. So signal of mutex, critical section, and again signal of mutex if they are using. So automatically any number of processes are allowed to enter into the critical section. So automatically mutual exclusion condition is not satisfied. Similarly, they use the signal of mutex, critical section, wait of mutex. So automatically it is not possible to come off. Already one process comes out of the wait function. So automatically again it's set to be the 0, no other process is allowed to enter into the critical section. So if we are using properly, that is weight of mutex, critical section, signal of mutex, then there is no problem. If the order is changed, then there is a possibility of the problems are arise. So automatic Semaphores is one of the software synchronization construct. If you are using properly, it provides a very good solution. If the programmer is not efficient to write the code using the semaphores, we get the problems are arise. So that is the limitation of the semaphores. In the next class, how to overcome the limitations of the semaphores, that is nothing but the monitors. We will discuss that one in the next class. Thank you.